Welcome, everybody, to today's talk by our own Shirley Ho. Shirley Ho is a group leader at the Center for Computational Astrophysics and has been there for, practically close to the beginning. 4 years, that's pretty good. Shirley's background, she got her undergraduate degree in Berkeley, double majoring in both physics and computer science. She became a graduate student in Princeton's Department of Astrophysical Sciences, where she earned her PhD in 2008, working with some guy over there. And she then became officially the Chamberlain and Seaborg Fellow at the Berkeley Lab, and then became an assistant professor at Carnegie Mellon University in 2011. And then after she became tenured faculty at CMU, she was recruited back to Berkeley Lab as a senior scientist, and then came to the CCA in 2018. Shirley has unsurprisingly won many awards over her career so far, including the NASA Group Achievement Award for her work on the Planck satellite, the Marcronix Prize, I don't know if I pronounced that correctly, or Macroni, is it French? Okay. The Carnegie Science Award, and it has been elected as a fellow at the International Astrostatistics Association. Shirley's work is just absolutely delightful to follow. She's really on the forefront in astrophysics, at least, at kind of merging the potential of machine learning with, deep astrophysical questions. It's less of a, I just grabbed this package and I applied it to my very simple thing Shirley has always been thinking about this stuff in a very innovative way and really trying to find the potential that merges, I think, machine learning with actual astrophysical insight as opposed to it just being kind of a utility tool. And so I'm delighted to welcome her for this talk.
Thank you. Thank you, Julian, for such a wonderful and delightful introduction. I hope this does not disappoint. For anyone who didn't know, I was in ER yesterday, so if this talk sucks, I was writing it with one hand connected to the IV, and I actually did find some serious mistakes. Like I spelled my student's name wrong, which I do know their names, by heart. So it's all good. So please don't complain too much. I have several students and postdocs here who are actually in the audience, and I will direct the questions that are too hard to them because I'm mostly just presenting all the work they've been doing. A long list here. I just want to show some faces for those who are wondering. More of the junior people who've been doing a lot of heavy lifting. Sharon Han at Princeton, Kimberly Stetcher, who's not so junior, she just looks young, from DeepMind. Pavel Lemos at Milan, jointly with Florence soon. Siyu He, who actually was here but left and went to Waymo. Miles Kramer at Princeton, Jacob Niebau, who's right there, Princeton. Alan Masser, who was here and moved to Waterloo. Joe Jameson, who was here as a pre-doc now at MPA. And Christian Jesperson, who's a Princeton grad student as well. So, agenda, and while you may not want to fall asleep, not yet at least. So I'll start with hype and some reality, and how do we look at deep learning as a last resort, which is the title of the talk. I'll start with the scale of the universe, which is what I'm actually going to concentrate most of my work on today in discussion, but I will touch on the next three, which is the scale of the Milky Way. Can we understand the properties of our own Milky Way? How about its potential field? Scale of our solar systems. It's not a last resort, but it's a great place that we can develop a really cool tool to discover other symbolic form and relationship. And the scale of our genome, can we guess why someone has, unfortunately, metastatic cancer versus primary cancer? So it kind of ranges things that we've been doing here. And so let's start with some hype. We've heard all the hype. So if I type this now into my computer, it says a neural network is a digital brain that lives inside a computer. That's what happens. It's an image generated by DALL-E when we humans just type in this line that says a neural network is a digital brain that lives inside a computer. I wish they made my talk last night, but that does not work. And if I input a teddy bear painting a portrait, you got a movie. It's fresh off the press yesterday. So I thought that was pretty cool. There's some people complaining about how the portrait is like 3D, but it's not 3D. It's a painting by paintbrush. There are lots of interesting things. You can hunt for snafus here and think of it as possible explorations to get better. For those who just arrived, we just showed this teddy bear painting his portrait. And the input to create this is just a teddy bear painting a portrait. So that was cool. And neural network can write its own code, or the clickbait version is that artificial intelligence can reproduce itself now. This is Copilot running in Visual Studio Code. And for those who does Sloan Digital Sky Survey, maybe not everyone here does astrophysics. You can literally type like function get dec SDSS, it will show up, which is kind of cool. The blue part is what showed up, not what we typed. We just typed like the other parts, which is pretty awesome. And someone claimed, I don't think that's necessarily true, someone claimed like 60% of the code right now on GitHub is written by Copilot. I don't know if it's true. I probably think it's not true because that's too fast. This is how I feel right now after reading all this. This is what is generated when I type a framed potato, a photo made of potatoes of a couch. And I thought, well, maybe they must make some mistakes, right? So I glanced through all this stuff, and I looked at one of those things. I felt, OK, I have something to do. A young couple walking in heavy rain. So that's the input, that's just text. Look at this. The arm had disappeared. They're like not just couple, they're like one person. So there must be a lot of things we can check, or for those who haven't seen it properly yet. You must notice some problems with this video that was just generated. I hope you feel, I don't know what you call those people who are connected, like born? Thank you, Siamese twins. So that's how it felt. So there are things to do, so I'm feeling pretty happy. So that's some realism for people to think about all the hype. So what do I do with all this stuff, right? These are just a couple recent examples that happened within the deep learning community. The video stuff came out yesterday, actually. So do we absolutely need this art or movie generated by neural networks? Maybe not so much, except for labs, or really cool for Twitter post. Or do we absolutely need this network to help us write code? My husband's a programmer, so he really doesn't like the fact that they can write code by itself. So it might get him no job. So I don't know. We'll see. This is a discussion we should have. But I would argue today there are situations where deep learning can be used as a last resort. And for my case, there's a lot of scientific applications. So that's the agenda today. So we start with the scale of the universe. Can we get the beginning and the properties of the universe? David can start sleeping because he's heard this 7 times. Some of us actually probably heard it many times. So let's start from that. So at the scale of the universe, this is a simulation generated by Illustrious projects. Some of the major architects are here, actually in Flatiron. And here's at the beginning. It's like 0.9 billion years after the Big Bang. You can see it on the lower left-hand side. And it's showing the blue dots of the dark matter simulations. And you can see that these dark matter particles interact with each other through gravity. And they kind of slowly get closer to each other, making bigger. So like metropolitan cities of dark matter particles, we call them dark matter halos. So we want to take this is the scale of the universe we're thinking about. And we want to know from what we observe today to understand the beginning of the universe and all the properties of the universe. So that was the grand question we're trying to understand. So how do we go from, like the left upper hand corner, which is like beginning of the universe at 0.6 billion years, to sort of like now, which is like 13.8 billion years since the Big Bang. So how do we connect that to that? And what is inside the universe? So that's the big questions a lot of us want to address here. And I will discuss that a little bit. So I will show work by a smaller group of us that started a little earlier. We call ourselves Symbolic, Simulation-Based Inference of Galaxy Collaboration. I don't know why we call ourselves collaboration. We just started with a group of people working together, and then all of a sudden we became a collaboration. What we showed here on top is that we have some observations. Oops. Do you guys see anything? No, I don't. Physical stick. I have observations, some telescopes. It produces the galaxy catalog. And then we want to use cosmological simulations and fully forward model and become like a galaxy catalog. And then compare the two of them and find these hidden parameters of the cosmology. These parameters can be the fundamental parameters of the universe, like how much dark matter there is, how much dark energy there is. Could be at the beginning of the universe, what are the phase distribution of the, all the particles. So it could be many things. So let's start from this part and why there is some need of using machine learning. So we actually, this group of us, have started doing this whole thing. And what we did at first is using this Coyote simulation set. Paco might be here. But he and his group generated a bunch of these. There's 44,100 simulations, trillions of particles, right? And if we move. But it's not enough, because we actually need a lot more than this to understand the beginning of the universe and all the properties of the universe. So what do I do? So that's tricky. So we actually think this might be where the last resort is used, because we want to accelerate the simulation by many, many, many times faster, because we need to generate a lot more of them. Here's the simulation you've seen before. And we have actually published 2019, that's a while back, a way to use deep learning neural network to push forward from a not very fast, not very, okay fast simulation to make it really, really accurate in some level. So that is the displacement of the network and its errors. Basically, the color is the errors. And you can see it's mostly blue, which is good. And this is the benchmark model at that point. And you can see that there's a lot of like not blue color. And you're like, OK, that's all right. It works well, and it actually accelerates the simulations by about 1 million times, which we thought was pretty cool. But it's not enough, because it does it only for one single cosmology. So it's whatever we trained on. It is within the training set. So we fast forwarded. This is just recently submitted to PNAS, where we had used it for all the different cosmologies. Sorry for all the plots for people who don't usually do this for breakfast. COLA is sort of like the benchmark that people use to run fast, large simulations. I'm just going to see all the words first. FNN is the fiducial neural network, which is similar to, which is the network we had run before, which is trained on one single cosmological set of parameters. So just one universe. And SNN is style neural network, which is what we did, putting in the style parameters, which are the cosmological parameter in this case, into all the layers of our network. And what are all the different y-axes? It's very easy. R is the correlation function. But this basically means the smaller the better, because you want to think of it as a noise power spectrum. Delta t over delta t true basically is the transfer function. Take the power spectrum of the simulation and divide it by whatever you want to divide. In this case, the true simulation you want to get at, and -1. So that's 0 is good. Larger than 0 is not so good. And same thing for density, displacement, and momentum of the field. So all the things that you care about in the simulations. OK, so that's the benchmark. And you can see that it actually shoots up very quickly beyond 0. This one actually behaves pretty badly quickly. And that's what the benchmark model. People have been using physical models. And that's what the neural network was doing. But it wasn't trained on different cosmology. This one, you enter the cosmology, and you just tell it, run this simulation, right? Our case, we used our neural network, and actually is much more stable than the other ones. These are the similar plots, except for something called a bispectrum. So the Fourier transform, or the 3-point function of the box for different triangles. Same thing. You can see that this model performed much better than the benchmark and our previous model. So we were pretty happy, and they're extremely fast. So we thought this is one case where the simulation acceleration actually is useful and is necessary, because what we want to do to understand our universe. All right, so now we have simulation that's fast for dark matter particles. We still need these shiny galaxies on top, right? We have dark matter particles moving around. How do we put these galaxies in? These are like the nice galaxies we supposedly look at. We can, of course, try to run this large simulation, very high resolution, very large volume. And when we mean large for cosmologists, we really mean very large ones, like that you can put in the universe. Hydrodynamic simulations. But these are very expensive. Each one of these simulations that I just shown is about 30 million CPU hours each. I don't have that much computer. And we need about 1 million of these, because we have a lot of different parameters we have to vary for not just cosmological parameters that are talking about the dark matter and dark energy, but also like, why is that? What happened when this supernova explodes? How does it impart the energy in the surrounding medium? What do we do with that? Like, that is super difficult to model. So these are expensive simulations. So now we said we need a lot of these dark matter simulations. Now we solve that. Can we skip using these hydro simulations, which are also very, very expensive? Or can we do something super simple, which is what we've been doing at some level? We call painting the galaxies onto the dark matter halo. So let's just remind ourselves that's the dark matter distribution. These are blue points. let's just find the halos. Halos are these metropolitan cities of dark matter particles. It's just like New York City of people, right? So that's the dark matter halo. I just find them, this is cartoon version. It's not the pretty one. The real pretty ones will be like much nicer halo that we find. And we need to ping the galaxies. So how do we do that? There are many different methods. I'm not going to go through all of them. I describe them as the simple one, which is the risky one, and some other methods. The simple one is try to use something like Higgs occupation distribution, some kind of analytical formula that does not necessarily take into account of all things, and we sort of marginalize over the parameters of the formula. This is actually what we're doing with the Symbolic collaboration I just talked about. There's a risky one that if you think there's at least one hydrodynamic simulations, and you have to know which one it is, that models the universe correctly in a smaller volume, maybe you can use many methods to learn from it. If you don't think so, what do you do? And I learned from Christian and Rachel actually sitting there, there's a lot we can do that's not those methods I just showed you. Here, this is the dark matter simulations. This is just to remind you, here is all these dark matter particles merging together. And when I say merging, it is important to notice that these dark matter halos will slowly merge into a bigger cluster. And they form something called like merger trees. So these guys merge to form this guys. These yellow ones merge to form this one with the next branch. And all that comes to today, this halo is this big. It's like New York City eating all the suburbs. Like as the suburbs getting eaten, like the city gets bigger and bigger. That's more or less what's happening. And we can use this information and put them into a graph neural network. And you're like, what is that? So here's Mangrove, Christian somewhere here. He's done this, which is to use dark matter halos, including all the merger trees, and using something called semi-analytical model to be like the true training set and test set with graphical neural network, and to populate these galaxies into dark matter halos. So what he does is that he first finds all the dark matter halos, he builds the merger trees, and he encodes these merger trees as an abstract graph and put them into like the features of the node. For those who don't do graphical neural network, it is, you can think of it as a graph where all the nodes have different node properties. In this case, it could be like different halos will have like masses of the halo, positions of halo, and what time it is, because the masses were dependent on the time, and the velocities and all that stuff. And the prediction, which you can regress from this graph neural network, which will come back in later part of the talk, is that you can regress to the galaxy properties you care about. Okay, and you can see there's many applications because there's lots of graphs in our real life application. So let's see how well Christian had done, and Miles actually. And so this is a traditional method we call abundance matching, which basically takes all the dark matter halos. The bigger dark matter halo get the bigger galaxies. That's basically the idea. And you can see that is the truth, and that's the prediction. And you see the spread is not so good. This is just one-to-one plot. So the thinner the spread, the better. And that's what Christian got. I thought that was pretty cool. He was pretty happy. So, and it happens for multiple other properties of the galaxies. So now we have a way to populate galaxies, not just number of galaxies in the halos, but also properties of the galaxies in the halos. So now we have some form of like creating the universe. I'm going to pause here and ask for a question. We just ran through very quickly a bunch of very hard concepts for those non-cosmologists. Yes, please use the mic though.
Is it on to use the mic?
I think so.
Yeah, now it is. Okay. Yeah, I don't actually understand this result right here. Like, why is this perfect match better? You mean it's a perfect correspondence to abundance match result?
The result is not perfect correspondence. The dashed line is the perfect correspondence.
I mean better correspondence, yeah.
It's a better correspondence than this one because it's way thinner, which means it's way closer to one-to-one for most of the galaxies. So here, the color is just showing how many galaxies are there.
Oh, you're just saying that the neural network matches the SAM better than abundance matching.
Yes, and the SAM is the truth here. So we're using the SAM as the truth. That's the prediction. Sure. So this is a prediction truth map.
Okay, thank you.
No, this is a good question too.
Yeah, can I ask when dark matter halos come together, and why do they stick together? Like, is there friction? Does it interact? If it were just point masses and there was non-interacting, I'd expect them to sort of stay in a big, hot kind of pool of them and not necessarily clump together and then clump together in this nice tree network.
There are many ways I can answer this question because we don't know what dark matter is and what the properties really, but we assume it's collisionless dark matter. And then, and you'd be like, well, they shouldn't be sticking together, but they just kind of move around with certain velocity with each other. So I guess merging is not that they're stuck. They actually just in closer. And then when they say in the same halo, they're just X distance away, so one handshake away from each other. That's one algorithm to classify as a halo. It's called friends of friends. We can go on and on. But then there's also the question of, we don't know what dark matter is. So it could have intrinsic properties that will make it move around faster, like warm dark matter, or maybe when they hit each other, they will annihilate with each other. So that's beyond my expertise. I was just going to let people who do dark matter properties actually answer more questions on that one. Yeah, it's a great question. Anything else? Yes?
This is more a very broad question of concept. So is it correct, should I think about this as, let's say, parameterizing the solution of a very large, complicated, nonlinear differential equation? I mean, in other words, if I boil down, for example, the evolution of the universe thing into mathematical terms, I have a model. Probably this is cold dark matter, so it's basically masses interacting via the gravitational force. I have a set of parameters that go into the model, the fraction of dark matter, of this, of that, the temperature. I have initial conditions, which are some kind of randomness. And then I have a process, which is encoded in the Einstein-Newton equations or whatever, that gives me a solution, right? Yep. And that the neural network is the job of the neural network basically to relate the initial parameters to the solution, including the noise.
Yeah,
Is that what the neural network is really doing?
So the network here actually does a slightly easier job. So instead of starting from the beginning, we use analytical method, which we know pen and paper can do it. Just linear evolution. First, take the linear solution and then get the nonlinear solution, that mapping, the residual from linear to nonlinear. That's what the network was doing for the first part. The second part of the network is to try to learn these complex hydrodynamic simulations, or not simulation, in this case, semi-analytical model, where the code is still very difficult and the equation is still very complex, and there's like not one single line to solve it, and just get that relationship as well.
But is the issue then solving a kind of inverse problem, so that you want to know, given a set of final things, which might be what we observe in the universe today, what the original parameters are up to noise? So it's essentially solving the inverse problem posed by that set of complicated equations, whatever they are.
Exactly.
Okay, thank you.
That's perfect. It's an inverse problem, but a lot of us are starting to do this forward modeling method, where you use simulations to do simulation-based inference, and going forward first, because it's non-trivial to go backwards. And people are trying. So, yes.
And when you are solving an inference or an inverse problem, so what does it mean to have solved something? What is the, so if it's a vector of parameters, what is the size of this vector? If it's an initial condition, how do you parameterize? So I would like to understand, what does it mean to have solved this?
Yeah, I think this is a great question. How do we know that we solved this, right? So initial conditions, first of all, it's just supposing it's some kind of random noise, but is it random in what way? Is it Gaussian distribution? Maybe slightly non-Gaussian. If it's slightly non-Gaussian, how does it look like? And the other question is, if I have a cluster here today at current time, what does it mean for the initial condition of the universe? Is there like a slight overdensity at that particular spot? So more like a phase space distribution at the initial condition.
What is actually unknown? So at the onset, what is it that you would like to have learned in the end when it's working perfectly?
So what is the phase space distribution of the universe at the beginning? Okay. And the components that's responsible for the evolution of the universe, right? So the dark matter, the dark energy, all this stuff that we don't know. Neutrinos, that's involved here, these light particles, what's the mass of these neutrinos?
So it's
latent parameters of this PD or ODE.
So how large is so if you were to describe the unknown, what is it? It's a vector of parameters, or it's a family of functions, or it's a distribution?
Yeah, we want to know basically of an array of numbers, and that array is really long for the initial conditions, probably at the order of millions or 100,000s. For the latent parameters, we're talking about 15, 20, because you also have parameters that we don't know about the galaxies, probably more, actually, to be honest. That makes sense, just to give an order of magnitude. Great questions. I hope no one else fell asleep. Okay, let's end in some reality, right? So reality part. We have telescope, we have detectors, and our own sky provide many extra blemishes to our theoretical universe. So here's an actual, telescope has observed these images. They're super blurry. This is actual images. We just made it into a movie. If you go from Earth and looked at, the sky, these are real images of all the real galaxies that are seen by Sloan Digital Sky Survey telescope. And you see that it's not what you expected. It's not all the pretty images that's in the box. No fly-through movies. And you see weirdness, like, parts of the sky is not observed. Do people want to venture a guess why parts of the sky are not observed by this telescope? There's the Milky Way, correct. We want overlocate the Milky Way. There are more reasons than that. Keep going. I know we have a lot of theory people here, but not so many. And competition, but no observers. Observer, we immediately, well, you can't point to the ground and look at the galaxy, look at the sky. That's one big reason. And there's a lot of chunks of the sky we remove that we don't think is good, so there's a lot of holes in them. And here's actually the observable we're going to try to observe. Try to compare to the actual simulation of the universe. This is, we call the Sloan Digital Sky Survey. It is, for those aficionados for this is the CMAS Southern Galactic Cap of the sky. The color tells you the time the galaxy is sitting in, so redshift of the galaxy. Okay, so this is what we observed. And we want to find is both the initial conditions and what's contained in the universe. And we created, can we play this? Somehow it's not playing. This is what we created with machine learning, not needed for the realism, but we use, for Symbolic, we used Quixote simulations, 44,100 simulations. We painted on it with halo occupation distribution, so like the simple method, and then we add in all the realism. Here's what we get. This one doesn't actually know, we're not using machine learning yet, but if we only have this, we cannot do what I described, which is get the initial conditions of the universe, which is an extremely hard problem. But for now, this is what we got. So, and the observations we showed you earlier, we actually don't need to use machine learning much yet because we kind of trust what the observations analysis have done, and we trust the catalog within the error that they give you for the systematics. So then the next part is, can we get the parameters? Can we compare the catalog, those two movie I just showed you, and actually find out what the universe is contained of? So how do we do high-dimensional inference given these two large data sets? So we don't actually have an answer yet, so I'm happy to be schooled here. It depends on exactly what you're trying to learn. So for a small number of parameters, Symbolic, which is what we have been doing right now uses machine learning-based method, in this case, mass autoregressive flows. We don't have to go into exactly what that is, but what it does is that it takes generated pairs of data and parameters and construct the posterior, the likelihood, and the joint distribution of the parameter and the data. So I don't know, you guys can guess. That's data, and that's the simulations of many different simulations. But they all look very similar because they have the right redshift distribution, they have the right sky realism, they all look the same. But this works for only a small number of cosmological parameters. What if you want to find out what happened at the beginning of the universe? That is not something we have solved yet or have figured out how to do it theoretically and even like on simple data sets, because there's a high-dimensional inference that is non-trivial. Let's just put it. I don't know the answer. I'm looking at like the people who do methods development. Maybe you can help us. So at the scale of the universe, let me just say what we have done so far. The ML has come to rescue at several critical points, accelerating dark matter simulations generation, so solving these differential equations a lot faster in different ways than what we usually do, accelerating the generation of galaxies, positions, and properties, inferring the posterior of our cosmological parameters using simulation-based inference techniques, using these mass autoregressive flows. So then we are like, okay, happy with the Symbolic. So that's the recap of the universe part. I'm just going to pause for any questions. Any questions or suggestions how to solve this high-dimensional inference problem? Yes, please.
Sorry.
He might just solve the problem.
Oh, okay. That's what I'm going to ask about, which is like, yes, how are you fitting the single real galaxy distribution to, like, how are you selecting the 15 parameters that match that best? Is that you're saying that's open work, right? I mean,
this is kind of, well, I mean, for what we do right now, we do mass autoregressive flow. What it really does is that you take all these simulations.
Yeah.
We have 40,000 of them or 20,000 of them that has different of these 15 parameters. Let's not talk about the million. Just do the 15 parameters,
that's
right?
Yeah.
Take that. So you have 20,000 of them. You have 15 parameters, those pairs, and you train a basically flows model. And then you create this posterior, and then you look at the data. That's basically it.
You just send it in. Okay.
Yeah, that's all it is. But there are different ways to do it. We also check it with traditional methods, like power spectrum, bispectrum, so 2 3-point function.
I think that's what I'm expecting. You'd find as many features as you can.
Yeah, we do all that first. We do wavelet harmonic analysis.
Right.
We do, so Michael Ackenberg and Bruno both doing it actually with us. We have Mark power spectrum, which is a special type of power spectrum. So we do all that, and then we also do graph neural network and convolution neural net.
Do they give the same answers?
Of course they don't, because they're taking different parts of the frequency. And that's why I haven't shown the result, because I want to check all the answers before I show all the comparisons. So far, the interesting thing is that the power spectrum provides similar results as like Mark power spectrum and wavelet. But they're not all the wavelet harmonics are used. So there's all these discussions like which wavelet harmonics you should be using and stuff like that. And then for the CNN and somewhat graph neural network, does similarly a lot better. But then we're like, okay, what frequency do you stop? Because for the other analysis, we stop at an earlier frequency at a larger scales. So you're taking in different information. So I didn't want to show the result partially because of that.
And
Next talk.
The simulations all seem to have a little gap in the same spatial spot. That seems weird to me. How were they all launched with the same initial conditions and slightly different parameters?
That's emptiness in that spot is because the telescope that we use, so the observed data has that gap. So we want to make it look like the telescope has that.
Okay.
Good catch. Yes, Evash.
If we were to compare this to heavy ion collisions, so that you have like
which I have no idea about, just warning.
Okay. I was going to ask like why those methods wouldn't work here, so we can discuss after.
Yeah, I have no idea about heavy ion collision. That's the problem. Any other questions? All right, I'll keep going. So this is moving away from the universe, getting slightly smaller scale. And next part, we talk about the Milky Way. Can we understand the properties of our own Milky Way? You're like, okay, we thought we knew that one, but actually we don't. How about its potential field? Do we know the potential field of our Milky Way? So here is something really pretty. And the Milky Way is supposed to be in the middle. And there's a stream. We literally call it the galactic stream. These stellar streams around our Milky Way. And when you see this stream, you thought about, what is that? Actually, Jacob didn't want to mention how this Milky Way. This is Jacob's work. These streams were created.
Sure, yeah. I guess the quick summary is you start with like a sort of bound ensemble of stars. And as it falls into the Milky Way, it gets disrupted by the tidal field of our galaxy. And a similar, you can make an analogy to how the tides work. One side gets tugged more than the other, and then that cluster starts to shed its mass in the form of stars. And those stars all continue on similar but slightly different orbits. And the result of that is you get this stream of stars that spreads out across the sky into something like that.
I can't do better than him, and he doesn't know I was about to ask him. So now at the scale of our own galaxy, so Gaia, which is this ESA telescope, has motivated new methods because they observed all these stars in the sky in our Milky Way, and very, very exactly and precisely. And we can probably go beyond the normal analytical methods. And what do I mean by that? So we have found all these new streams that we just show, the shell structures of our Milky Way, and want to use these as tools to understand the property of our own Milky Way. And we ask ourselves, like, why do we care about the Milky Way, right? Well, the Milky Way has something like dark matter halo. Remember, we have this like metropolitan city of dark matter particles inside also. And if the dark matter properties were different, the Milky Way should have a different potential. And I think and I hope that this will actually open up new avenues to understand the dark matter properties. And people have done a lot of work in that direction. I'm actually a newbie in this direction. And since we actually don't know the correct analytical form of the potential of the Milky Way, the traditional methods actually don't work here as well without the strong assumptions, now that we have much better data. So neural network actually fully enables this full data-driven potential reconstruction without these assumptions. And we talked about why we care about Milky Way potential. So let me show you this. Can I pause this without? OK. So this is on the left-hand side. It's a single simulated stream in the angular coordinate in the plane of the sky. Just think of randomly looking up in the sky. You have phi 1, phi 2. And we're going to scan across phi 1. And here shows the energy of the stars and angular momentum of the stars in z-axis. And we want to show you that something kind of fun. As you scan across, you see that the distribution of stellar orbits along the changing angular coordinates is actually evolving quite slowly. So they all kind of move together, right? So they have similar energy as like nearly a Gaussian distribution sometimes, and similar angular momentum, but they're not the same as you move along the stream. But they're evolving slowly across the stream. And with this central assumption, we can do many things to look for these streams. I don't have my notes here anymore, so I'm just going to go blind and try to explain what's going on here. So we have these streams here, and we try to order data nicely. And with neural network, you actually can find this phase-based parameter of gamma. And this is actually very important to find this phase-based gamma, which will, if you look at the previous stream, it will be like the phi 1. It's like scanning across the stream. And why is that important is because you want to parameterize the stream as a 1D path. And in order to get to the 1D path, it's good to find this phase-based variable, gamma. And it relates to x and the position and the velocities very well. And maybe Jacob can even explain us even better than I would here. And with all these, this is where the neural network work. And once you can actually find gamma, you are able to estimate acceleration much better. There's a loop here that's going on. And find and explain to us what acceleration of the whole Milky Way is. And once you have acceleration, you have the potential of the Milky Way, which is used as a secondary step. All right. So I'm not going to go through all this again. But basically, the point is that Gaia motivates these new methods for describing Milky Way beyond using analytical models, which is what people have been doing before. We're treating a stream as an ensemble orbit where the localized movements, the measurements of acceleration is possible. And the localized acceleration measurement can be combined at the likelihood level so that you can get at the global potential of the Milky Way at the end. But it's inferred as a post-processing step because you actually get the acceleration field. And the neural network actually lets you do it fully data-driven without these assumptions. So now you can do complex mass densities of the Milky Way. You can have dark matter substructure, which will come in very important to understanding the dark matter potential. All right. I don't know, Jacob, do you want to add anything here? OK. This is very difficult, because I was trying to read his paper yesterday. That was the plan. But reread now. OK, so next part. At the scale of our solar system, this is not a last resort thing, but it is a really cool tool that was being developed at this scale to discover other symbolic form and relationship. And then we actually use it for other things, which I'll show you later on. And you're like, at the scale of our solar system, so we looked up in the sky. Can we predict what happened and infer the rules? A lot of you guys probably have seen similar talk here, which I or Miles have given. So I'm not going to go through all the steps and details. So time t equals 0 and t1. Traditionally, we look up in the sky and say, OK, maybe we'll be like Newton. This is the famed apple tree of Newton's manor, like the actual apple tree. Don't know whether he actually got hit by apple, but there was an apple tree in his manor. Or if you're not Newton, we would do something a little bit different. So I argue that maybe we do something called symbolic regression. And what is symbolic regression? It's basically a search of a huge range of mathematical functions. You can insert what's the range of mathematical functions you want and the variables. We form new equations, and then we check whether these new equations fit the observables every time. We move on to the next new equation to find better fit. And it all sounds very good. You find new equations, that's symbolic, right? But the possible issue is that it cannot really search a really large space for the right equation because it's very expensive. So what do? What we did is that we combined neural network and symbolic regression to extract the rules of our system. We used a neural network, but in particular, we used graph neural network, which you heard before from Christian's work, to make sense of the system and help predict the dynamics first, before we even go forward and interpret the network. Okay, let's take a pause here. The network just compress the data. Once it's compressed, then we feed it to symbolic regression, the search tree. We can probably do these things much more efficiently and combine together and optimize together, but that's like the next step that Miles haven't done yet, but he's working on it. Okay, let's make sure that we can predict the dynamics properly. And here's the result. Here's the outcome of 1,000-step rollout of true versus predicted. True on top, the model at the bottom. And you can see that there's n-body interactions, balls bouncing four walls, strings falling onto this blob here. I can describe to you where all the nodes and the edges are, but for those who haven't done this before, haven't seen me talking about it, the strings have these nodes or these little dots, or these mass balls, and the edges are what's connected, the balls, or the little mass balls. And for the n-body, it's a fully connected one, where all of them are connected to each other with all the edges. So that's the graph. Seems like they work quite well. And we even did zero-shot generalization to larger system, which basically just means I have not seen the system before. My network has not seen the system before. I just ran it. And you can see that they do OK. The balls in the four walls is the most terrible one, in my opinion. It's actually really hard to do. But you can argue that the network has learned something to be able to predict quite OK for something that it hasn't seen before.
So I have a question, Shirley. So
Please.
For the n-body, I imagine that you are looking at.
Do you use the mic? I can't hear you.
I think I'm using it. Yeah.
Okay.
So for the n-body simulation on the very left, I imagine that you are looking for gravitational interaction potentials. Okay. So for the balls, what is happening there? It looks like you are ballistic, and then you have just hard.
It's like the what do you call? We're playing pool basically,
Yeah,
but for
but
bouncing.
how do you know that there are no interactions between the particles and only interactions between the particles and the walls?
No, that one we have a fully connected graph. So all the balls interact with each other, and it also interacts with the wall. So the wall is
but
one
they
node.
interact only upon contact. So you have only contact forces. Do I understand it correctly?
We don't know, actually. So the network doesn't assume you only have contact forces.
So I'm curious about what is it that the network has recovered in the middle case?
I don't know the answer to that one, because we did not recover this one. We did not even try, because it didn't actually do super well, as you can see. Because like at the end of it, you can see like the balls are not in the right place. But we do recover that one and some of the strings. But this is a good question. What do you recover? We should try it, actually, because we could do it.
But such, I mean, definitely so there is plenty of potential here for deterministic chaos. So what does it mean to have recovered something?
This is a good question. So we recovered. So let me finish describing like what we actually done afterwards, and you see like what has been done and what can be easily done. But I think this can be recovered. The question is like, do I know the answer to this myself, like just independent of the neural network?
Shirley, before you keep going.
Yes, please.
Could you just reorient me again? So there's Newtonian mechanics in the true. What's the difference between the true and the model?
The true is a simulation.
Right.
You just ran a simulation.
Right, but using Newtonian
Like just traditional
Right.
methods, yeah. And the model is the simulation. Well, not the simulation. Sorry, the network has seen a bunch of the simulations at many, many time steps.
taking snapshots.
Yes, snapshots of them. And then it's modeling the whole thing as a graph neural network. So for this one, it will be a fully connected graph. So it'll be a node, like a lot of nodes of, like, say, each little planets in the sun. And then there'll be connected edges. But we don't know what the edges has said. It's just an array number, right? So the network figure out what the array of numbers should be to produce the next time step position and velocity of these balls. So that's why when I say answer stats, I mean, the network doesn't know what the edge is supposed to say until it's seen the data. It's only got the right number in the edges to get the right next step. That's all it has to learn. Yes, Romain, you have to press the button. You're far. I definitely can't hear you.
Can you hear me? Yeah. So isn't the true discovery of Newton the law of action and reaction? And is your network architecture assuming this built in? And so you don't really rediscover this first principle law of nature. You impose it on the network architecture. And so if you start from a much more general framework, I don't know what could be there, but it would be interesting to see if you find as an emerging result the law of action and reaction.
Yeah, so we do have to somehow assume there's an action-reaction, right? Because actually, we just assume there's some kind of relationship between the two balls.
Exactly, that's the hardest thing, right?
Yeah, so
That's
that is actually, this is actually what the referee asked us. So you'll see later on we discovered the Newton's law, but it's not you the referee. I was like, maybe Romain has refereed the paper. But then they're like, well, but then in our abstract, we even said that we cannot assume without the action-reaction. We actually have to assume it because of the way this is structured. And the referee asked, what if you remove that assumption? Like, can you do that? Can you still discover this? The other question the referee asked was that, what if you haven't discovered mathematics? So like, how do you describe the data? So I did not answer that question. Don't out yourself as referee, though. So now we can predict dynamics somewhat. We try to understand what the network has learned. So here's what is actually fairly simple code. So what we did is that we have some data. We have a network that has made predictions, compare with the data again, and update the weight. Once you do that, you have these edges, you have the nodes, right? You record the messages on the edge. The edge can be a pretty long array. It could be a bunch of numbers here. But we actually need to force it to have as few things as possible, because remember this tree search thing, which is we call symbolic regression, doesn't do well with large numbers of parameters. So we want to make it really, really small number. So we use something called L1 regularization, which is basically just try to make it has as little number of elements as possible down here. And let me describe it by words a little bit more. Given the input simulation is only 2D in some of these cases, we do not expect the dimension of the edges to be larger than 2 at first, so we try that. But once we did that, we limit it to 2. We immediately makes the training longer, and the performance not as good. So imagine you just make it into like MLP, like 2 elements, basically. And then we use L1 regularization, and we honestly try a bunch of regularization technique to minimize the number of message elements that are important to fit the observable to the predictions. Then once we did that, then we put the edge element that's remained through the symbolic regression and see what we fit for the 2 elements or a few elements. And so that's what we did. But just note of caution, this L1 regularization doesn't always work. There are other things that we have since then that we use non-L1 regularization. We have to discover like new ways to regularize. So we found the force laws from observing 2 systems, the Springs law in 2D and 1 over R squared law in 3D, which we were pretty happy about. So to conclude, at least for now, we think we developed a symbolic regression-based interpretation method called PySer. This is a package that's freely available to anyone who wants to work on it, for distilling and discovering symbolic models from deep learning, and in particular using graphical neural network. So we thought we want to just double check if it works with some real data. So maybe Romain's not the referee here, but we took the NASA Horizons ephemeris data, which is basically orbits of 30 years for planets and moons. Take all of them. And we use actual orbits from 30 years observations, do the whole shebang, which includes putting it into nodes, and then you have all these edges. And we use symbolic regression. We find the Newton's law, and we even found all the masses of the moons and the planets along the way. And let me just describe what they are. These are log of the masses in solar mass unit. These are the names of the planets, names of the moons. Truth being the star, circles being predicted. You have multiple circles because we want to start with different initials and initialization. So just to get a sense of like error distribution. And you can see that they're actually quite bang on for all the planets. The moon's not bad. And you see some errors here, which actually makes us happy, because the errors in the mass prediction actually is quite nicely inversely proportional to the gravitational influence that it exerts to the system. So for really light things in that system, it doesn't change very much of what anyone else is doing, so you should have a large error bar. And that actually plans out. So we were pretty happy. So now we've seen the universe, the Milky Way, our solar system, and I said, well, that one, okay.
Have you guys identified how many conservation laws do you have?
Say that again, I can't hear you.
Do you know how many, so let's say you succeeded in fitting the dynamics. Can you say how many conserved quantities you have, and whether these conserved quantities are actually what they are, which are energy, angular momentum, and
there is a piece of work that inspired that list of work that we've done by Schmidt and Lipson from 2004 or 6. Actually, Lipson is actually a Columbia faculty there, and they'd actually used similar ideas, but back then, neural network's not neural network now. They found these conserved quantities, and you can actually do that in many methods that people have been looking at conserved quantities. And we have another paper that called Lagrangian and Hamiltonian neural network, using the conserved quantity to predict the dynamics instead of using those quantities directly. Yes, please.
You learn that you make a graph neural network learn the dynamics before you feed it into the symbolic regression machinery. Is there a special reason why you just can't feed the data into the symbolic regression and then get all of the nice expressions out of that, or is it, or not?
The symbolic regression doesn't do it with like a large, amount of data. So until we can figure out how to do it really well there, I think it's going to be difficult. This is like one thing, like how do you search quickly and optimize with large parameter set and large data sets? It's tough. That's why the neural network was mostly to compress and condense. Yes.
Yeah. So I had the impression that if I take a large number of gravitating bodies and I run the simulation for an infinite amount of time, their trajectories will become totally chaotic, and that there's an intermediate time in which they're more or less regular. Are these simulations over the intermediate time where they're more or less regular, and would I be able to learn the gravitational law if I ran them over the time where the dynamics become totally chaotic?
This is an extremely good question. We actually wrote a different paper about can we predict the instability time scale of any planetary system, and also use a neural network. Most of these rollouts become unstable after a certain number of steps. And it doesn't matter whether it's neural network or non-neural network method. They all become, crazy. And this one, actually, 1,000-step rollout is pretty impressive already. There's a lot of network that was, they will show you what they have, and it's like actually 15 steps, and it's actually good for that 15 steps. But afterwards, it goes haywire. And we have done a bunch of work in sort of turbulence simulations, where when we were able to do it for 160 steps, we were very happy.
Great, but that was a much smarter question than what I asked. But
okay.
my question was just if the numerical data I have, or the orbit data I have, is for a time interval where the orbital motion is totally chaotic, would I be able to learn Newton's laws from those data sets, or do I need to be in a regime where things are more or less nice orbits?
This is also a very important question, actually, because what we did is that for some of the orbits becomes chaotic, we actually remove those deliberately because they don't produce good training set. It just went chaotic fairly quickly. And so you only retain those who have long rollout. So that was the practical answer. Cool. So take these two that we just described. I have hopefully not so much time left. It's only 2 slides later. At the scale of our genome, can we get why someone has, unfortunately, not very cool things to say, metastatic cancer versus primary cancer? This is work with people at CCB, CCN, CCA, so very happy about this. So what is primary versus metastatic cancer with graphical neural network and symbolic regression? So as we've seen earlier, we have developed a symbolic regression-based interpretation method for discovering symbolic models. So now we want to take a look at applying this and modeling a whole genome mutation pattern in tumor patients. Why? Because most tumor patients die from metastatic cancer that originated from the primary cancer site that display basically clinically aggressive phenotypes. Phenotype is like what exhibits from the genome. So being able to tell between the metastatic cancer and primary cancer is very important for the treatment. So we want it to be also quantitative and somewhat trustworthy. So maybe deep learning is the last resort. They're like, what? So that's what we did. We built a graph neural network inspired by this tissue-specific gene regulatory network for the people with CCB, please explain to me what they are, but we follow something called the reactome pathways. So what it does is that all these genomes, and you sort of group them according to what these reactome pathways telling us how they might be related. We group them into subgraphs, and then we connect them back to this sparsely connected layer, and then we want to predict whether it's metastatic or primary. And then we apply PySer to the graph neural network. So okay, before I finish saying that, once we build the subgraph, it performed at least as well as a state-of-the-art model, and we hope that it will get better. So, but we haven't trusted the result yet, so we don't want to show that yet. And then we apply PySer, which is the symbolic regression technique that we showed you earlier, to the graph neural network, and now looking at generating symbolic equations that analytically determine the metastatic prostate cancers from patient-specific whole genome mutational signatures. So that's what we're doing. You should talk to Chris Patterson, Frank Drew, Steve Fletcher sitting right there, TB, Miles, Olga about this work. I'm mostly learning from the side and trying to apply this algorithm to this data set. So just want to show you we can do it from the larger scale of the universe to our own genome. So I thought that was pretty cool. Conclusion, not sure I have one. Deep learning can do a lot, but some of it is not as obviously necessary as the other, but some can be useful. So this is used stable diffusion for those who are aficionado in this machine learning world. This is using similar technique, not exactly the same. Ronan, is it using stable diffusion still? Okay, maybe something's related. And he's using it to generate the cosmological simulation of the universe. Instead of couch potatoes, we got the universe. So that's my conclusion, and thank you.
Hi, we don't have a tremendous amount of time for questions, but luckily we took a lot during the talk. So we'll have a couple of questions, and then just to remind people, there's a reception on the rooftop afterwards, and I've seen pictures of the signature cocktail. Looks pretty good.
I haven't seen it. Hi, yes.
So in the second to last application, where you're doing symbolic regression.
For the solar system?
Yes.
Okay.
You're showing uncertainty amongst the predictions.
Mm-hmm.
And I was wondering, is there an interpretable notion of uncertainty on the functional space?
Oh, on the functional space. This is something what Miles is working on, actually. Trying to get distribution of equations that you can predict. So you talk about the functional space of the equations, right?
Yeah, so if I had a posterior distribution of
on
the functions.
equation space, yeah. So that's what he's working on. But for these masses predictions, you can get errors. There are different methods to do it. And I'm sure you know, like Bayesian neural network, you can do stochastic weight averages. What we're showing here is just changing initial conditions. And people have done dropouts as well.
Mm-hmm. Okay.
Yes, please.
A naive question, but when you're trying to solve for the initial conditions of the universe, can you use information that we already have, like CMB data? Because you're not really trying to learn the initial conditions without any other information.
Very correct. Yes, we do want to do that. We actually want to analyze both the CMBs. This is, for those who don't do cosmology, it's cosmic microwave background, which is the baby footprint of the universe. We want to use that and the larger structure at the same time. So that's the goal, but we want to do it one side first successfully and together when we get better at this. All right. Is Sophia raising your hands? No, just. Okay.
Yeah, were there any questions on Zoom?
There are no questions on Zoom.
Amazing talk for myself.
Everybody was just, I think people were distracted by the notion of cocktails. So let's just thank Shirley again.
Thank you.